Hey guys, I am back with another video lesson. So, we are doing right triangle trigonometry today. Right, but before we get started, there's something on the homework that I did want to go over. So, a pretty, I guess, semi-common mistake I saw on assignment number 1 was in, let's say, a 30, 60, 90 right triangle. Some people had a hard time getting the other two side lengths when the longer leg was given. Right? It's very easy when you're given either the shorter leg. For example, if I gave you the shorter leg was 10, I know it's the shorter leg because it's across from the 30-degree angle. Right? Then it's easy to find hypotenuse. That's 20, twice the shorter leg. Right? And the longer leg is going to be 10 radical 3. Right? Radical 3 times the shorter leg. So the problem I was seeing was when they didn't give you the shorter leg or the hypotenuse and they gave you the longer leg, some people had difficulty getting the other two legs. So for example, let's say this side length was 6 and you had to find the length of the hypotenuse. Well, we're going to use the same relationships that we saw when we derived our special right triangle relationships. And that is, in the 30, 60, 90, that the hypotenuse is equal to twice the length of the shorter leg, and that the longer leg is radical 3 times the length of the shorter leg. Excuse me. So, in this case, I have the longer leg, and what I would do is, with the longer leg, I'd probably find the length of the shorter leg first. So if the longer leg is equal to the square root of 3 times the length of the shorter leg, well, couldn't we say that the longer leg divided by the square root of 3 is equal to the shorter leg? Right? And if you want to see that algebraically, well, all we have to do is divide both sides by the square root of 3. So in this example, the length of the shorter leg is going to be 6, the longer leg, divided by the square root of 3. And if we rationalize that, multiply by radical 3 over radical 3, we're going to get 6 radical 3 divided by 3, which is equal to 2 radical 3. Alright, so that's the length of the shorter leg, and our hypotenuse would just be twice that, which is 4 radical 3. Alright, so that's that. That was just something I noticed. But moving along with today's lesson on trigonometry. Before we start, what is trigonometry? So, trigonometry is really just the relationships between. Trigonometry is really just the relationships between the angles of a triangle and its side lengths. So, what I mean is, that's what I mean. Right? Trigonometry is just relationships between the angles in a triangle and its side lengths. Right? And we start with right triangles because that's a little easier to work with. But trigonometry, it could be for any kinds of triangles. So, with trigonometry, you might have heard of SOHCAHTOA before. And yes, that is what we are going to start with as well. Right? And if you've never seen this before, well, you're going to see it now. These are just some definitions for the relationships in right triangles between their angles and their side lengths. So before we do SOHCAHTOA, let's draw a right triangle. And there's a right angle. So in trig, or really in a lot of things, whenever you're naming an angle, it's very common to use this symbol. Excuse me. And that symbol is theta. So that symbol, if you haven't seen it before, that is called theta. Right? And some people like to draw a circle with a little line through it. I draw mine like that. Right, so anyway, if this is our angle theta, in relation to angle theta, well, we're going to have some names for these side lengths in relation to angle theta. So always across from our right angle in a right triangle, this length we know is called the hypotenuse. what do you think the side opposite this angle is going to be? Well, we're going to call that the opposite side. And then this next side length that is next to data, in other words, adjacent to it, we're going to call that the adjacent side. Right? If you're just thinking in English, yes, the hypotenuse is also adjacent to your angle theta, but that already has a very special name. That's called the hypotenuse because it's across the right angle. So there is only one adjacent side to this angle theta, and that's this guy, the one that's not the hypotenuse. So the adjacent side is going to be the non-hypotenuse side of the triangle that kind of forms the angle, right? These two side lengths form the angle, and the adjacent one is going to be the one that is not the hypotenuse. Right? And of course, all of these names change, well, at least two of them change, depending on where we put theta. So if I make theta over here now, for example, well, this side over here, now that's my new opposite side. My adjacent side would now be this guy, right? The one that's not the hypotenuse. And the hypotenuse still, as always, that will always be across from the right angle. Right? And angle theta is never going to be the right angle. Angle theta will always be one of these two acute angles in a right triangle. Right, so back to SOHCAHTOA. This is a way to remember some trig definitions, and these definitions just have to do with the relationships between the angles again and the side lengths in a right triangle. So the S stands for sine. And sine is going to be the relationship between the opposite side length over the hypotenuse. So we say that sine of an angle is equal to the opposite side length over the length of the hypotenuse. All right, C stands for cosine, and that's going to be the length of the adjacent side over the length of the hypotenuse. So that is COS, the abbreviation for cosine, is equal to the adjacent over the hypotenuse. And lastly, TOA, that is going to be tangent, and that is opposite over adjacent. Right, and the abbreviation for tangent is tan, and that is opposite over adjacent. All right, shout out to tan for tangent. All right, so those are our three trig definitions. And you might be asking me where they come from. Well, these are just definitions, so I can just give them to you. They don't have to come from anywhere. It's just what we defined as mathematicians as some relationships. All right, so sine is the relationship between opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent opposite over adjacent. So that is SOH, so, CAH, Ka, TOA, SOHCAHTOA. All right, so that's a pretty useful trick. So let's just practice on, let's say, this right triangle here. If I call this triangle ABC, pause the video for a second and tell me, if you can, what sine of A is equal to, what sine of C is equal to, what cosine of A is equal to, and what tangent of C is equal to. All right, so sine of A, that means we're looking at this angle right here. We know sine is opposite over hypotenuse, So if we're looking at this angle A here, the opposite side is going to be side BC. So sine of A in that triangle would be the ratio of BC over the hypotenuse, which is across the right angle, AC. And that's it. All right. Do not label BC the opposite side, because when we look at sine of C now, for example, right, BC is no longer the opposite side. Our opposite side is now AB. So again, opposite, adjacent, that's all dependent on your angle. So if we're looking at angle C, opposite is again AB. And our hypotenuse is still our hypotenuse, that's still AC. Right, cosine of A is going to be the adjacent side, which is not that one. Cosine of A, again this angle, right? You might think we have two adjacent sides, but one of those adjacent sides is the hypotenuse. We do not want that one. Our adjacent side here is AB. And that's going to equal AB over hypotenuse AC. And yes, you might notice that these two are the same. We will talk more about that later. But that is something cool to notice. Right? And tangent of C, so now angle C, that's going to be opposite AB over adjacent AC. Sorry, I keep doing that. Adjacent is not AC. AC is our hypotenuse. If we're looking at angle C, our adjacent side here is BC. So sorry, AB over BC. All right, good. So those are just some definitions. All right. So coming down here, given two right triangles with right angles C and F. So let me mark these two as right angles, C and F. Determine if they are similar. Side length values are approximate and rounded to the nearest 1/100th. Round all values to the nearest 100th. All right, if you want to try this for a minute or two, go ahead and pause the video, see if you can tell me whether these are similar or not. All right. So, if triangles are similar, then we know CSSTP. Corresponding sides of similar triangles are going to be in proportion. So, I can see if these sides are proportional, right? At least to the nearest 100th, because everything's rounded. So, for example, if I do AC over BC, right, this leg over that leg, that should equal this leg over that leg, right? Shorter leg over longer leg. That should equal DF over EF. So if I do 4.63 divided by 9.49, and let's see, is that equal to 7.35 over 15.07? Put a question mark, because I don't really know. So hold on, let me type this into my calculator. 4.63 divided by 9.49 and 7.35 divided by 15.07. To the nearest 100th, these are both approximately 0.48, or sorry, 0.49 if I round. So yeah, those sides are in proportion. We should also check with the hypotenuse and something else. So if I do the hypotenuse of triangle ABC, 10.56 over, let's do the shorter leg, is that in proportion with the hypotenuse of our bigger triangle over, what did I use, the shorter leg, 7.35. And let me check that out. So 16.77 divided by 7.35. And if you do both of them, they're both going to be the same proportion, around 2.28. So seeing that the sides are in proportion, I can confidently say that yes, these are similar triangles. And so if measure of angle ABC here, if this guy here is 26 degrees, then this is also 26 degrees. So to answer the first question, yes, triangle ABC is similar to triangle. If I call that ABC, I gotta call this guy DEF, right? Because corresponding sides of similar triangles are in proportion. So So, from this, well, we can say something like, if I take a look and that's 26 degrees, then can't I say that the sine of 26 degrees, well, remember, the sine of an angle is equal to opposite over hypotenuse. So looking at 26 degrees, the opposite side is 4.63. Sine of 26 is going to be 4.63 divided by the hypotenuse, 10.56. And again, let's type that into our calculator. 4.63 divided by 10.56. And that is 0.44, approximately. All right? But if you type sine of 26 into your calculator, of course, you're also going to get 0.44. So, quick thing before using your calculators. Well, first of all, if you don't have a calculator, get it out. I will wait for you. On your calculator, to get your trig functions, that's going to be next to the number 7. It says the word trig on it. So if you hit that button, you'll see sine, cosine, tangent, and then also the reciprocal trig functions, which we will talk about later, and the inverse of those. So there's really 12 trig functions here on your calculator, but we're only going to worry about 3 for now. So click that first guy, sine, and type in 26 in the parentheses and hit enter, and you should get 0.44 as well. Right, so that sine, that is the relationship between the ratio of the opposite to the hypotenuse in the right triangle. Wow. Should be the same. And sorry, if you're not getting the same answer, that is probably because you are not in the right mode. So in your calculator, if you look at the top right, it should say DEG. Make sure you are in degrees. Right? If you're not sure how to change your settings to degrees, hit the on button on your calculator. Right, go to settings, choice 5, and then go to document settings, choice 2. And then under angle, change that from radians, if you're in radians, to degrees. All right, and then if you go back to your document, you try a sine of 26 again, you should get 0.44. All right, and if you take a look at the bigger triangle, in this bigger triangle, well, sine of 26 would be, again, the opposite, which is now 7.35, over 16.77. And again, if you type in the sine of 26, or 7.35 divided by 16.77, you are going to get approximately 0.44 again. And that is because, well, these are similar triangles, so of course, corresponding side lengths are going to be in the same proportion. Right? So these trig values for sine, cosine, and tangent, they're going to work for any right triangle, as long as the data is the same as the angle is the same. So let's just do one more set. For example, if we know that's 26 degrees, well, we can find the missing angle. 90 plus 26 is 116. And then 180 minus 116, what is that? That's 64 degrees. So for example, if we do, let's do tangent this time. And let's do tangent of 64 degrees. Well, that's going to be the relationship between opposite over adjacent. So that's going to be 9.49 over 4.63. So if you type in either tangent of 64 around 2.05, or if you do 9.49 divided by 4.63, you get about 2.05. Same thing would be true in this bigger triangle. If you took tan of 64 degrees, opposite over adjacent, right, you divide these two guys by each other, you would also get 2.05. Alright, so these trig relationships work because as long as the theta in your right triangle is the same, right, all the sides are going to be in proportion because two of the angles are going to be congruent, right, that angle theta and the right angle. So that ratio of opposite to adjacent or opposite to hypotenuse or adjacent to hypotenuse, it's always going to be the same ratio. And those are our trig definitions and relationships we're going to be using. All right. So one more thing is if I draw an XY plane and I draw a circle centered at the origin here. All right. And let's just draw a radius in the first quadrant anywhere, like so. All right, I can draw this radius anywhere, as skinny or as tall as I want it to, but I'm going to draw it, I don't know, somewhere over here. All right, and then from that point, I'm going to drop a perpendicular to the x-axis. So what we have here is a right triangle. So if I call this arbitrary point I picked x comma y, well, let's think about the side lengths of this triangle. If this point here is x comma y, doesn't this length have to be x? Right? If that's not making sense to you, let's do it with numbers. Let's say that point is, I don't know, 5 comma 3. Right? If that's 5 comma 3, wouldn't you agree that this length here then would be 5? Right? And that length there would be 3. So if it's an arbitrary point, like x comma y, well, that length will be x, and this length here is going to be y. All right? So let's call this angle here now theta. So remember, sine of theta, sine of any angle, is the relationship between the side opposite the angle over the hypotenuse. So the side opposite angle theta here is going to be a length of y over the hypotenuse. So this hypotenuse was a radius of the circle. So let's call that r. So sine theta will be y divided by r. Right? And solving for y, we can say r times sine theta is equal to y. All right, let's do the same thing for cosine of this angle. Cosine of theta would be the adjacent side, which is x, over our hypotenuse, which is r. And again, solving for x, we can say r times cosine theta is equal to x. And these are two really important relationships we see. So on a coordinate plane, x comma y, we can say that is the same thing as, well, we saw x was r cosine theta and y was r sine theta. Right? This is probably quite a bit for a lot of you, but the main thing is I want you guys to see that any coordinate x comma y, right, on the Cartesian plane or the coordinate plane can be written as r cosine theta comma r sine theta. Right? And we got that using our definitions. All I did was opposite over hypotenuse and adjacent over hypotenuse. And this is something that's really important. Cosine theta, that's going to go with our x value. And sine theta, that's going to go with our y value. All right? So the main takeaways I want you to get from this lesson is this as one of them, and just knowing how to use SOHCAHTOA. Not really use it, but just what it is, actually be able to calculate it. Right, we're just starting trig. I know this is like completely different than pretty much everything we've done all year so far. But again, these are just definitions. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent's opposite over adjacent. All right, so that is going to be it for today. Just looking through the notes one more time, seeing if there's anything I want to add. But yeah, I think we're good. All right, so this is what you need to know from today. An assignment's going to be posted on Classroom. And have a good weekend, everyone. So assignment's going to be due Monday, I guess.